this last section of the notes for 9.9 is going to talk about a couple of other ways that you can mess with series to get new series. So, for example, if I'm trying to get a power series that represents this, we could definitely take multiple derivatives and expand it from there and see how that goes. That actually would not be too bad, because the power rule would work pretty nicely with this. But another way we can do this is recognize what the antiderivative of the desired function is. So let's start with that, because they give us a hint of looking at the antiderivative of the desired function. And I think we're going to see that this is going to be 1 over 1 minus x, right? You can do a little bit of u substitution to verify that. Yeah, we've got the plus c. So that means that if I have this fraction right here that I'm after, but I know what this Taylor polynomial is, then I can just work backwards. I can un-anti-differentiate, which is differentiate, to get there, right? So I know that the derivative of 1 over 1 minus x is equal to the thing that I'm interested in. Well, but I also know all about this, because I know that this can be written as a geometric series, right? Because we know that the sum from n equals 0 to infinity of a times r to the n is equal to a over 1 minus r, provided that we have our x values between 1 and -1. So if I replace this fraction with this series, I know that this is equal to the derivative of the sum from n equals 0 to infinity of x to the n, which is the same thing as the derivative. If you're not sure, my mantra is when in doubt, expand it out. The first term is 1, the second term is x, the third term is x squared, the fourth term is x cubed, and you just keep on going forever and ever, right? So we can definitely take these derivatives. These are the easiest derivatives we could hope for, I think. 1 goes away. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. And that just keeps on going and going and going. And what we can see is this is the same thing as the sum from n equals, well, let's hold off on that equals for a moment. Looks like we're going to have n times x to the n minus 1. Looks like we could start with n equals 0. But that would be a little bit weird because we'd have a 0 term. So let's go ahead and start with n equals 1. Either way is fine, right? And we find that this is exactly the same thing as the thing we started with, this 1 over 1 minus x quantity squared. All right, so that's the first 3 non-zero terms. Maybe I'll expand this out a little bit more. Get that fourth non-zero term. I guess that'll be 4x cubed. All right, so one thing we'll find here is that when we integrate a power series to obtain a new series, we're not going to change the radius of convergence. Okay, so this radius of convergence of 1 for the original series is going to be the same as the radius of convergence here. We definitely know that the interval of convergence is going to be very close to, if not exactly the same as, -1 is less than x is less than 1. The only thing we have to remember here is that it's very possible that the convergence at the endpoints might change. Okay, so right now we're excluding, like from the original series, we're excluding the endpoints. But we're going to, because this is not, just using the power series, we actually did some new stuff to it. We took the derivative. It's possible that the endpoints might change. the behavior might change. So let's double check. We're going to check the endpoints. Check the endpoints. Endpoints being x equals -1 and x equals +1. All right, so we're going to use this and we're going to plug in -1 and we're going to look at the sum from n equals 1 to infinity of n times -1 raised to the n minus 1. This is an alternating series, but the individual terms don't converge to 0, so this diverges by the nth term tests. Diverges by nth term tests. All right, so don't include -1. So we'll check +1, and we're going to find that, of course, the fact that it was alternating didn't stop it from converging. The sum of 1 plus 2 plus 3 plus 4 is obviously going to diverge as well for the same reason, for the nth term test. So it diverges by nth term tests. So in this particular case, we had to check the endpoints, but we noticed that we're still going to exclude them. So our interval of convergence stays exactly the same. So this would be our final answer. Now, one thing that we've seen in the past is that taking the derivative of functions can lose parts of the domain, right? We see that with functions like y equals the cube root of x, whose domain is all real numbers, but is not differentiable at x equals 0. We see that with y equals the absolute value of x, whose domain is all real numbers, but is not differentiable at x equals 0, right? So we've got functions whose domain is one thing, but then when you take the derivative, their domain is something less, right? We lose values of the domain. We can never gain values when we take the derivative because functions, continuity is a prerequisite of differentiability. So based on that same idea, we kind of already knew that taking the derivative of something was not going to add to our interval of convergence. It can only take away. So if you knew that, then we wouldn't have had to check the endpoints. But you know, it's still a good habit to get into, to check your endpoints. All right, so differentiating can lose endpoints. Integrating, on the other hand, might gain some endpoints. So let's see what happens on this one. Set that one up for an exciting foreshadowing, didn't I? Again, we're going to start with this hint that the integral of 1 over 1 minus x, we should recognize this to be negative the natural log of the absolute value of 1 minus x. Right? Yeah, we got the plus c, whatever. That's not exactly what we're interested in, but it's very close to what we're interested in. How about we divide both sides by -1? And we'll take negative the integral of 1 over 1 minus x dx is equal to the natural log of the absolute value of 1 minus x. All right, well, that's going to be negative the integral of, well, this is the exact same function that we're familiar with from before. The integral of this power series, n equals 0 to infinity of x to the n dx. And if you're not sure how to expand that out, or to take the antiderivative, let's, when in doubt, expand it out. We got 1 plus x squared plus x cubed plus dot, dot, dot. All right, so we'll have negative, taking the antiderivative of this, we get x. Taking the antiderivative of this, we get x squared over 2. Taking the antiderivative of this, we get x cubed over 3. We're just doing the inverse power rule all day long, forever and ever. And I'm going to go ahead and put that plus c actually here. Okay? So this is actually going to be the same thing as c minus the sum from n equals 1 to infinity of x to the n over n, right? X to the 1 over 1, x to the 2 over 2, x to the 3 over 3, x to the 4 over 4, etc. So that is apparently what the natural log of 1 minus x converges to. All right? Well, let's deal with that c value. I'm wondering if we can pick a nice, comfy value of x. Like, let's let x equal 0. Okay? So if we let x equal 0, we get the natural log of 1 equals c minus 0. All right. Well, natural log of 1 is 0, and c minus 0 is c. So actually, c is just equal to 0. So la-di-da. We can just ignore that. All right. So anyway, we've got this natural log of 1 minus x is equal to negative the sum from n equals 1 to infinity of x to the n over n. Now remember that our interval of convergence started out as this. Now we're anti-differentiating that. So when we take the antiderivative, it stands to reason that we might gain values on our endpoints. So let's see what happens here. We're going to, again, check the endpoints. Oh, this is exciting. We're going to try x equals negative 1. Remember, we know our interval of convergence is definitely at least negative 1 is less than x is less than 1. But we might actually include an endpoint or even 2 if we're lucky, fingers crossed. So anyway, we're going to check negative 1, and we'll plug that in to our series. And we'll get negative 1 raised to the n over n. Wait a second, I recognize this. This converges conditionally, but it converges because it's the simple alternating harmonic series. I can't spell. Alternating harmonic series. We recognize this one as a famous one that we don't have to prove. If you feel like proving it, it's not so bad. We can use the alternating series test. Okay, so that means that because this converges when x equals negative 1, we want to include that little bitty bar right there is the whole gaining here that we got. And then we're going to try x equals positive 1, and I think we can recognize that when we take the sum negative, the sum of 1 over n, we know that this is going to diverge because it's the harmonic series. And again, this is the famous one. This is the simple harmonic series. Simple harmonic series. You can call it a p-series. It is a p-series. So because it diverges, x equals 1 is not part of the domain. So our interval of convergence includes negative 1, but not positive 1. Okay? So that would be, one of the ways we can use integrals and derivatives to create power series without having to actually do the multiple derivatives over and over and over again.